All right, everyone. This is Matt Yost here at GL. I'm going to go ahead and get started on our webinar. So thanks for attending. So welcome to our May 2017 edition of our monthly webinar. And the title of today's webinar is Evaluation of Public Address Systems for Mass Transit Applications. And what we're going to do today is basically provide a very, very high level tutorial on these evaluation methods that are used and that GL uses with our technicians and our engineers and so forth. And we definitely here at GL can get a little bit deeper and a lot deeper into some of the theory and some of the procedures that we follow while we do these tests. But for the purposes of this webinar, we're going to keep it pretty high level. And just a very quick overview of the company. GL Communications was founded in 1986. We're headquartered in Gaithersburg, Maryland, in the USA here. And we have our companies consists of basically two divisions, we like to say. They're complementary divisions, and one of them is a consulting services division. So engineering consulting services. We typically help out mass transit agencies and government organizations, but we also do private sector work as well. The other division of our company is telecom testing products, which we have a whole suite of off-the-shelf telecommunications testing products, equipment, anything from protocol analysis in the TDM or VoIP domain to echo cancellation testing to voice quality analysis and so forth. So we've got software and hardware products, a whole division of our company dedicated to doing that. Our customers, again, include on the product side, really anybody in the sort of the research and development labs for the carriers. We're talking Sprint, AT&T, all of the network equipment manufacturing companies like Cisco and Ditech for echo cancellation, and a lot of other companies that make equipment. Also a lot of service providers, of course. So it's just a little overview. Today's agenda will be an overview or just a little bit of a background on PA systems and how they've evolved, existing public address system conditions, what do we run into when we typically show up on site to do an evaluation of a system, and then the evaluation methods. Okay, so the heart of the webinar will be about, if we're called out to do something or someone is called out to do an evaluation of a PA system, sort of what methods do you use, and what are the procedures to do those things. So we're going to talk about visual inspections, operational checks, sound pressure level, speech transmission index, which is kind of the heart of the matter here, and transmission network, so evaluating the transmission network from point A to point B. And then the final thing, sort of post-processing, where we can do some acoustic modeling. So we're going to touch on all of these things, again, at a pretty high level, but feel free to follow up with questions where we can get into some more details with you. So again, the background here, where we started, and where I'll kind of set the foundation here. Over the past couple decades, the PA systems have definitely evolved a little bit, and they've added safety and security features. Obviously, safety, security is a very hot topic. It has been for a few decades now. Even before that it was, but I think the evolution has changed a little bit into these PA systems that mass transit administrations and agencies have sort of taken their focus away from operational information, even though they still do that, to a lot of safety and security concerns and making sure that they are alerting their customers, their patrons, when in the event of an emergency, evacuations, some sort of things like that, real-time information. Some of these changes, as mentioned here, there's been a tie-in to fire system evacuation, and these have been mandated by local and state governments. here in the U.S. and in other countries. So many of these locations, I'll say, have older PA systems. So and they've fallen victim to time and environmental elements. So you've got an old system sitting out there. The sun, the weather, all of these things play a factor into how they're going to operate long term, and obviously the effectiveness of that system will be altered. So, and one thing I'll mention before I move on here, after the first bullet, I kind of failed to mention that, you know, these rail stations or platforms or large airport areas are the examples of what we're talking about here. They play an important role of alerting crowds. So that's kind of going to be the focus here. I'll use an example throughout the whole presentation on maybe a rail station, or, you know, a platform for a rail station and so forth, just as an example. It is also possible that the original design, okay, so whenever this PA system was designed, let's say in the 80s or even before that sometimes, it was not designed in an adequate manner, okay? And so coverage may be a problem, intelligibility may be a problem, so forth. The original design did not meet sort of today's standards, we'll say. And even on top of that, new designs, new installations, maybe they're meeting the spec per the theoretical spec on paper, but somebody may be required to come out and test those just to make sure in the field to see that the installation meets the spec. Those types of things are needed, and some agencies require that. So that's sort of where we're going to go with this, and that's where we're focusing today. So again, an overview. So what we're talking about here is, you know, when we talk about PA system evaluations, what are we evaluating? It's fairly obvious to some, but just to state it here, we're talking about coverage areas. So does your location that the PA system is intended to cover, is it adequately doing that? Are at a rail station, are the platforms covered completely? Are the ticketing area, is that covered? So even administrative offices behind, you know, closed doors, locked doors, they require the PA system to cover them. So are we covering the whole area? Is the quality of that coverage good? Okay, is the intelligibility good? Is the clarity good? So these are the types of things we're going to be evaluating. And, you know, on top of that, and it plays into all that, system audio levels, the ambient noise adjustments. So a lot of systems, as you probably know, have ambient noise microphones that will feed an AGC to lower or increase the volume of the PA system. So is that all working correctly? Has it been actually configured correctly to work correctly? Let alone a problem in the field of a degrading component. Has the system been designed correctly or even configured on site correctly? So these things, you know, are typically what we would run into. On top of that, transmission network operations. So from point A to point B, you know, you may have a control center, we'll just call it, at a transit agency needing to give a live message to a station out on the line. So first of all, how is that audio transmitted from point A to point B? Evaluating that, what network is being used. In some cases, radio networks get used if it's going to a rail car or to a bus or something like that. So the quality of that network obviously plays a factor in the intended audience hearing it correctly. So how can we evaluate that transmission network, we'll call it. And then physical inspections, just, you know, looking around to see if things have been properly maintained over the years. So when we show up on site, or if an evaluator would show up on site, what are the existing PA conditions? So again, we mentioned earlier, or I mentioned earlier, about older designs and older equipment. You know, you'll typically run into it, especially with government agencies. You know, the funding has just not been there over the years, and they've got a system in place. It's been in place for a while. It's an older design. It's got older equipment. Some of those things are breaking down. The faulty components plays into that. So speakers are obviously, you know, on everyone's mind first. Are they breaking down? You can kind of see in the picture to the right here where you've got some cracks and so forth. It's not even that bad, but it's the start of some possible bad things happening down the road. So there's all types of things that can be faulty in a PA system, from the cable, the speakers, the ambient mics not working, even just lack of preventative maintenance over the years, people not monitoring the system properly. Things get a little bit out of whack on all levels. Okay, we're talking physical level, operational level, and so forth. So just doing a full evaluation of that is what may be needed. So one other thing that comes into play, especially prior to recent decades here, is, you know, the building materials that were used at a station or at a airport or something. They may not even be conducive to a PA system design, and they actually may be detrimental to your patrons, your customers, being able to hear correctly and intelligible from the PA system. So no consideration was given to the PA system during these building material selections. And then, of course, you know, a major factor in a lot of these types of mass transit locations is noise, external noise. So we're talking about road, train, or people noise, crowd noise, things of that nature. You know, if we're talking about a train station, usually they're open air on the platforms, and you've got typically in cities, so you've got a lot of background noise going on, as you can imagine. How does that play a factor into the customer actually being able to hear the PA system? It obviously does. And what improvements could be made to help that? Okay, so we'll talk a little bit about some of these things. Even with existing modern complex systems, okay, there's a lot of, you know, cutting edge sort of PA systems that have just been installed in the last few years. Now, where we found that problems may happen there is not necessarily in the design or the materials or the components. They're fairly new. It's typically with the configuration of the system. Now, maybe the installer did it and they say they've done it right, but it always is a good idea to have a second set of eyes look at it if you're having problems at a location. DSPs can be configured wrong, ambient mic levels can be configured wrong, things of that nature. So even complex new systems have issues, and they're typically due to configuration. So when we talk about the PA evaluation methods, we're going to get to the heart of the matter here. These are the things, as I talked about in the agenda, that we'll focus on today. Sound pressure level, what is that? Visual inspections and operational checks. So what are we going to do when we're on site? Sort of the heart of all evaluation for PA system has been sort of adopted as the speech transmission index, or the STI measurement. And then the transmission network and some of the quality of service algorithms that are associated with that, and acoustic modeling. Jumping right in here, just talk about sound pressure level here for a minute and what that is. A couple definitions for that. The difference between the instantaneous pressure at a point in the presence of sound, of a sound wave, and the static pressure of the medium. So what we're saying there, or second bullet, local pressure deviation from the atmospheric pressure. The diagram here, just to show it graphically, number one in the diagram is during a silent condition, of course. So we've got no sound pressure. So completely silent, atmospheric pressure is there. During audible sound, okay, audible sound does not need to be somebody coming across the PA system giving instructions. We're talking about background noise, all types of things. That is shown in the horizontal direction on number 2 on the diagram. So 3 is a representation of the atmospheric pressure. Okay, so no sound around. That's sort of what you get from the atmospheric pressure. And then the sound pressure deviation, the highs and lows there on number 4 on the diagram, shows you the sound pressure level. So graphically, this is where you're measuring sound pressure. So what does sound pressure mean? You know, obviously, if you have a high sound pressure, then it's a high noise environment. During a lot of background noise is present, so your ambient background noise is high. During the PA announcements, it should be higher, of course, because you're trying to get across the message to somebody. So just this is a fundamental sound pressure level. What is it? And just graphically how it's being shown. So continuing with sound pressure level, when you show up on site, you know, you've got to make a lot of these measurements, and sound pressure measurements are definitely relevant and need to be made at each testing location. So we'll talk a little bit about defining the testing locations, but right now we'll focus just on sound pressure level. Sound pressure level measurements of the ambient noise, so in the presence of just background environmental noise, you want to know what sort of the baseline is at your testing location. And then during, we'll call it a signal. So during an announcement, during the presence of a very true announcement, or during the presence of a testing announcement that we use, okay? Call that the nominal PA announcement of the testing signal level. And then with those two things, you can get a signal to noise ratio, and that's just the ambient, or the signal minus the ambient, okay? The SNR and dB there. So with sound pressure level and with a sound pressure level meter, one can individually check speaker operation. So if somebody would like an evaluator to come on site at their rail station, you know, one thing for sure is to make sure that all speakers are at least operational. So you can use a sound pressure level to constantly be checking, go to each speaker. There's, in the picture, you'll see behind the gentleman who's actually got the meter, you'll see sort of a telescopic sort of pole there that you can attach the sound pressure level to, and you can put it right near the speakers, and you'll get an idea if the speaker's actually working. Now, when we get into STI measurements or speech transmission index measurements, it's going to be pretty obvious if a speaker's not working when you start reading these values on the STI. But this is a good way to just do a spot check on all. I wouldn't say a spot check, just a verification on all speakers that they're operational. When the field crew's there, it's a good idea to do. Let's just say that. And the SPL measurements it's an important measurement to take prior to doing STI testing. And why is that? Because STI testing needs to have the SPL at a certain level and so forth. They're critical clues, these types of measurements at all testing locations for engineers to decide, post-processing, deciding what improvements may be recommended for a location. So again, sound pressure level, very kind of fundamental here on how it's used. A sound pressure level meter can be used at a site to get a good understanding of the operational environment. When a crew shows up on site, you know, you want to make sure that they're doing a visual inspection and some operational checks. So again, with the sound pressure meters, going to each speaker is a very good idea while you're there. When I say each speaker should be visually examined, you don't need to do what the gentleman in the picture is doing, which is unscrew each speaker and check it from that perspective. But a general look at each speaker to see that nothing is obviously wrong with it. Do a check on its sound pressure level. Okay, that's just a fundamental check that each speaker is possibly working. If a speaker is not working, it obviously should be noted on the drawing. And then all of this information will feed an analysis of the system. And I'll show you that as we move forward here when we get into acoustic modeling. So it's just a general visual inspection and operational checks of all PA components. Now, so we're going to get to the heart of the matter here, and I've said that before, but this truly is what the evaluation method of choice has become in the PA industry here. It's called STI measurements, okay, or speech transmission index measurements. And before we jump into what those are, I'll step back for just a second and talk about sort of the intelligibility of speech at transit locations will depend on a couple different factors, of course. I mean, we can list a few of those things, and here they are for you: the acoustical properties of the surrounding physical environment. So, what materials are your walls, your floor, your ceiling, and some of the sort of retaining walls? Other things? Is it an open air rail station? What is the surrounding physical environment? And how does that play into how your PA system is functioning? Okay, so that's obviously step one, is finding out what those things are from a CAD or from an on-site inspection. What is your background noise? What is the road, the train, the people noise? What is typical background noise at this location? And again, these things can be measured, sound pressure level meters and so forth. And the PA system design. What type are we talking about here? I mean, is it zoned? Is it not zoned at a location? The quality of the system components, and have they been properly adjusted, configured to operate as per, you know, how they were intended to be operating? So these are the types of things that can factor in. When we talk about the speech transmission index with the STI measurements here, these are testing methods for measuring speech intelligibility. It's been widely accepted. It's a widely accepted algorithm in the PA system community. And I'll give you a little history on that on the next slide. But it basically, one sentence of summary, the STI predicts the likelihood of syllables, words, and sentences being comprehended by your customers, by your patrons. So, and it's from a 0 to 1 scale, 0 being the worst, 1 being the best. So STI meters are used. They can be on site. Some of the testing procedures for doing evaluations at a location I'll talk about a little deeper in the coming slides. But as an overview right now, these STI, one thing to take in, the STI measurements is sort of the widely accepted method of evaluating a PA system. The testing is performed by transmitting a reference signal known as a STI-PA signal or a STI-PA file, and through the PA system and measuring the STI at every desired target location. We'll talk about how you pick the locations to measure, sort of grid by grids and so forth. These measurements usually are taken by a handheld device, and each measurement can be executed in 15 to 30 seconds. Again, I think we'll talk about a little bit more on how that's done in the coming slides, so I'll just leave it at that for now. Some of the history from STI and where it came from. It was first theorized back in the 1970s, early 1970s, by a couple of Dutch fellows, and I think they were in the military is what I read. And they ended up working for this applied scientific research, this Netherlands organization. So that's where it kind of came from there. And it's been widely accepted recently for sure. It's always been accepted in the acoustic community, but with PA systems and so forth, that kind of came around in 2000-ish time frame. Sort of how it works is it utilizes modulation transfer functions in the acoustic domain. Okay, so I'll leave it at that. There's a lot of math behind it that we can get an engineer. If you're very interested in diving deep into that, we can talk about it. But at this moment, I think that's sufficient. The STI scale, according to the standards body here, is shown in the chart below. at the bottom. And again, it's an STI value from 0 to 1, 0 being the worst, 1 being the best. And they've put a range on what bad, poor, fair, good, and excellent is. And then you can actually see what the prediction is on how many syllables, words, and sentences can kind of be intelligible to a person. So it's just a chart that shows that different jurisdictions, agencies try to design per a certain STI value, and I'm not gonna say what that is because it can be different from one agency to the next, and sometimes it's unreasonably high, I would say, for the environments that we're working in. But this is sort of the general chart here for what STI values you're going to get and what they're generally considered. Okay, STI had a derivative come out, like I mentioned, called STI-PA, so it's a public address. That derivative was introduced in approximately 2000, and that's been standardized by the IEC, and edition 4 of this STI-PA is the latest release. It's currently the accepted standard. That is what somebody who is evaluating your system should be using, the edition 4 STI-PA. Okay, so just wanted to state that there. This STI-PA allowed STI measurements to be taken at such a faster rate than the traditional approach, and for how that happens is it uses impulse response method versus the previously modulated voice method. Okay, so without getting into anything deeper on that, I just wanted to state there that it's using the impulse response method, and what the bottom line with that is a technician can show up on site and actually take measurements in a lot quicker fashion than they used to be able to. Accuracy and speed is very attractive to technicians and engineers. It's very conducive to locations in transit. Portable testing equipment has emerged, and there's quite a few of them on the market nowadays for that. As we see here with a couple examples of that. And I just picked a couple, no offense to if anybody's viewing that makes a piece of equipment. I just picked a couple here from NTI Audio and from STI. They just show you just a couple pictures there of what they are. On the right-hand side, it's one of our field technicians is utilizing one of these instruments and doing STI measurements. Okay, so just wanted to show you that. Now, when we're in the field, how these measurements are done, and are they done sort of per the standard is a very important question. Each location is generally divided, I'll say generally divided, into 400 square foot testing grids. So within each grid, multiple measurements are performed, and what we would do is a testing crew, like our crew, would adhere to the standard recommendations of averaging and discarding measurements. So once you're in your grid, you're going to be taking multiple measurements in each grid. So you set up, let's take an example of a station platform, a rail station platform. You set it up into 400 square foot grids, okay? And then your testing team would go to each grid, take multiple measurements, throw out a couple if they're outside the range, average the other ones, adhere to that standard, and then record those things. The field measurements by our team are recorded manually, and they're automatically by the testing instruments. So it's a good idea to do that. It helps for post-processing in case there's any questions and so forth. You can see on the right-hand side, it's just an audio survey data sheet which shows handwritten tests at different locations. Okay, it's not, just wanted to throw it up there. The one in the foreground is, after that we transfer it to electronically and we put it in our report. So it's just an idea of how we're doing it. What are we taking at each location, at each testing locations? Well, we take the SPL, and we start with that. What's the ambient? What's the signal SPL? And then we take STI measurement at each location. Any relevant notes that the technician may want to write down. For instance, the background noise is being caused by X, Y, and Z, so forth. So it's a good idea to do that, take a sort of a real-world approach to what's causing some problems possibly. And then in the post-processor, phase of this, in the analysis phase, if improvements need to be suggested for a certain site, some of those notes come in handy on where, what improvement may be suggested. I'll just say that. And as we mentioned earlier, individual speaker operational tests are done. Okay. That kind of is the it's all we're going to say about STI measurements for now. We'll get back to them here shortly a little bit more when we're doing post-processing of that. The next couple slides are basically about the transmission network. So here's a very, very simplistic diagram of maybe a control center on your left-hand side sending a message, maybe a pre-canned message. Sometimes those are stored at the central place. Sometimes they're stored locally at the PA sort of intended location. Or maybe the PA system has live message capability, which they typically do these days, and you can, during an emergency, someone could pick up a phone or something and send a message to a remote location. So the transmission network is what I'm focused on with this slide, the next slide. And how do you evaluate that transmission network? Because your PA system, all functional elements may be operating 100%. If your transmission network has some problems, then it at least should be evaluated to rule out that as a problem. So that's what I'll mention here. Centralized control, and I just basically mentioned these things with the diagram, but I'll briefly say it again. An example of a centralized control center would be a rail operator control center initiating a live emergency announcement to a remote station on the rail line. So what does the transmission study include? Well, it's an end-to-end voice quality measurement. And what we do here at GL, there's multiple methods to doing this, but we find that the best method is actually do a true end-to-end voice quality measurement using telecommunications industry standard algorithms. We call them voice quality algorithms. And those are defined by the ITU Standards Board, P.862 for PESC and P.863 for something called POLCA. And what that does is it's a true end-to-end voice quality test. So you inject audio at one end, typically the control center end, and you record audio at your intended target. So that could be the rail station. And you just compare the two files in a sense through this algorithm, and it gives you a quality score. Now, that method is nice in the sense that it's truly end-to-end. It doesn't necessarily matter what you have in the middle. So you can have a traditional TDM network on T1s or E1s or something, or you can have an optical network, or you can have a radio network. It doesn't matter to this evaluation method. It's just a true end-to-end on the quality of the audio. This same product, this method of doing voice quality analysis is utilized across the industry, anything related to voice, so cell phone carriers, anything. So they use the same method. Just wanted to mention that. Here's a couple screenshots of that software. On the left-hand side, you actually can see there's what I had mentioned at the bottom there under the manual measurement tab. You can see a reference voice file and a degraded voice file. So the reference voice file would be the clean file that you send into the network under test. The degraded file is the one that you record on the far end. A comparison is made and a score, an industry standard voice quality score is produced. Okay, that's what we'll say there. There's a lot of other measurements on the right-hand side top that are performed at the exact same time on these two files: level, clipping, jitter, things of that nature, all can be shown. Now, bottom right, I'll just briefly mention, this thing can be tied in with GPS, and this evaluation of voice quality can be done. Let's say you have a rail line or a train that is, going from point A to point B, and you've got a PA announcement that can be played on the rail car, right? Let's say you have a live announcement where there's some emergency that you want to play audio to the rail car. Well, that's a moving rail car, of course. We can put a GPS receiver on our recording side, our degraded side, and basically we're evaluating that system as it moves along the rail line. So we're able to, and what that does is, most likely in that case, it's a radio network that's transmitting the audio from point A to point B, and you're evaluating that radio network. And it can show that on a map, just as we're seeing here. This is actually a drive test around the Baltimore, Washington area. But yeah, the capability is all there. Okay. Last bit that we'll talk about today, and then we can jump into some questions. And I see that I've been going pretty long here. It's 40 after the hour. I'll mention acoustic modeling. Okay, what is acoustic modeling? This is kind of a post-processing method that is very effective when improvements need to be recommended, okay, to an agency or something, or a PA system. So after we do all of our field measurements, we bring all those back to the office. We throw them into a model. We try to represent the station or the PA system effectively in a software, in a model. So what are the inputs to that model? Well, the physical dimensions of the location, the environmental conditions, where the background noise is, all the speaker locations, all of the speaker models, the orientations, all of that plays a factor. We're very well versed in running these acoustical model softwares. We use, for instance, this one called EASE. Now, it's a standard one that can be used for acoustic simulation. The accuracy of the existing locations model is critical when recommending potential changes to the system. So what I mean by that, and I'll harp on that a little bit as we move forward here, what you first have to do is you have to draw your model of, let's say, a rail station and platform. You draw your model in this CAD program, and you enter all these dimensions, speaker locations, all this stuff gets entered into the model. Then the model itself produces the expected STI values, okay, for that location. Now, what you have previously done, or what we've previously done, is we've had our field crew out there actually measuring the STI values. We bring those back, we compare them to the model. Is the model correct versus what the real world is? Yes or no? We make a couple tweaks. Maybe we forgot something. Maybe maybe the material is different than what we thought it was. Things of that nature. So everything is verified. We try to get that as the model as accurate to the real life station as possible. We have our baseline for our model. Then what we can do is, and this is sort of showing that, just a drawing of the model here, a rail station acoustic model where we've drawn it, we've entered the location of the speakers. It's now predicting. You can see sort of the concentrated area that's basically right below a speaker, and your STI values are represented across that model. This is, I would assume, maybe a ticketing area or something like that. Now, verifying that this model is correct versus your field measurements, like I mentioned, is very critical when we move ahead to improvements. Okay, so an agency, government agency, or transit agency will ask you to evaluate their system, and then At the end of that, we can dump them a report that says, here's what your system looks like, we're done. Or we can say, here's what your system looks like, and here are some recommendations on how you can improve the quality of your PA system, X, Y, and Z to do that. Okay, now how do we do that? We typically will do this acoustic modeling method where we'll draw our model, make sure that it's an established model for accuracy, and then we may tweak some things within the model and see how the STI measurement gets improved. So what you have at that point is you have a model that you can maybe add a speaker to certain locations and see how that affects your STI. You can change a material. Maybe the ceiling material is not conducive to PA system, so you can put in some acoustic tiling and so forth. So there's a variety of things that can be done, and they can be simulated within the model, okay, and then shown to the customer to say, here's what we expect if we do these couple improvements. Okay. Last thing I'll mention there is, from experience, we've noticed that moderate improvement costs can result in STI gain. So simple little changes can result in fairly significant gains in STI value. But if you go to the extreme there, making a very large, expensive improvements, the sort of reward for that is maybe not necessarily it's not a linear reward there on STI gain. So some simple improvements, adding a speaker here and there, lowering the heights of speakers, changing some the ceiling material, adding a couple panels to block out environmental noise. These types of things can cause a tremendous improvement in your STI values. And that's represented here, sort of in our final couple slides. The one on the left shows a location where you can see the existing STI values, and then the improvement by adding just one speaker. You can see that a speaker was added there in the middle, and you've got some improvement on that. It's what would be expected. It's fairly common sense, but now in the model you can represent it and you can show it, and you can predict what quality increases, what STI value increases you'll get before you even step foot on site to actually make any of these changes. Okay. One other example of that is here, where on the left you have your existing STI values, and on the right we've added some acoustical tiles in the ceiling, and this represents the change for that. So pretty significant increase in STI values at this location. I think I've mentioned this a little bit, and this is kind of my last slide or two, but some example of system improvements: replaced defective speakers. Obviously those would be recommended if we found that. Installing additional speakers, generally that's backed up by an acoustic model simulation, and levels is typically found on site to need some adjustments. I'll leave it at that, and even lowering some speaker heights in some ceiling areas. If you're in a sort of a cathedral area where you have the speakers are very high, maybe lowering them will help. And some of the materials, even adding glass walls in open air locations. Okay, typically agencies will not want to close down an open air location because that's very pleasing to everyone, customer-wise, but adding a glass wall or something can be very effective in allowing sunlight to come in, but also blocking out environmental noise, traffic noise, and so forth. So sometimes those are recommended. So the last thing, I think what we did today, and just right before question and answer here, I will just review very quickly. We went over what PA system, what we run into for existing conditions and so forth, and some of the evaluation methods that we use here at GL. And with that, I'll leave it at there. That concludes the webinar on the instructional part. Any questions we'll try to answer at this moment. I hope you enjoyed the webinar, and feel free to definitely contact us. I do realize it was a fairly high-level webinar, and if anyone would like to have some more detailed information on how things are done, what methods are used, we can definitely provide that to you. So,
Yeah, thank you, Matt. I have a couple of questions.
okay.
One is, how long does it take a crew to perform the field testing?
Okay, that's a very good question. That will obviously depend on the size of the location that we're testing, but what we've found from experience is once we get on site and have some cooperation on site from the agencies and so forth, for instance, at a rail station, we'll say, you know, typically you'll need an escort, you'll need to arrange all of that stuff, and once all those sort of bureaucratic things get settled, once we show up on site and we have access to the system, we usually take a half a day, I'd say, to a typical sized rail station with platforms to do STI measurements. At times, you know, you may need a day if it's a large station, has a big ticketing area and large platforms and so forth. So it kind of depends, but once you get moving with the agency, it typically goes a little quicker from station to station. Okay.
Thank you, Matt. Another question we have is, can you explain operationally how the transmission study is completed?
Sure. Okay, so talking about the transmission study, so again, what we have there is typically a test of the network between the control center and, let's say, the remote rail station out on a rail line. And what I had mentioned is a method that we use, which is a voice quality algorithm that's been very widely accepted and standardized by the telecommunications community. PESC is the name of it, but that is an end-to-end voice quality evaluator algorithm. So what that will do is that you can inject audio at the control center, we'll call it in this case, and then you record the audio down at the station. Okay, where do you record exactly? Well, that's kind of to be determined at times, but we have equipment that recorded many different interfaces there. So we typically strategically find a place we record. We evaluate by sending a voice file through that network. We evaluate how does that voice quality get through there, how does and what if there's some degrading factors, what are they, and sort of how bad are they, and then maybe further investigation after you've got the number can be done, and then we can ask questions to the agency. So what are you doing here? How is that being done? And then usually the problem kind of surfaces. I will say that the transmission network, unless it's a radio network, is generally pretty solid at these at transit agencies. So typically problems occur locally to the speakers and the amplifiers and all of that. So, but it's a good idea to do it. Okay, it's a good idea to do it at times. Okay, info@gl.com will if you have any questions, you want someone to give you a call and we can discuss some more details about this offline. We'd definitely be happy to do that. All right. Well, thank you everyone for attending. I hope you enjoyed it, found it a little bit informative, and keep checking our website for our monthly webinars. We'll be advertising what the June webinar will be probably in the next week or so. Okay, thanks a lot. Have a good day. Bye-bye.